Okay, good morning. Today is my third lecture on, let's say, the general features of particle detection and reconstruction at the LHC. In the first two lectures, I gave you glimpses into what is needed to put together an apparatus as complex and performant as what is required to do the physics at the LHC at high luminosity. We talked also about with Maxim Titov and also with some experience from my own experience in Atlas with the transition radiation tracker about gaseous detectors a lot. I will talk a little bit more about tracking detectors today. I would need 2 more lectures at least to talk about calorimetry, about muon detection in some detail. So this will leave to some other lectures. I believe you will have lectures on silicon detectors, I think, and also on calorimetry. So you will cover everything which is required to build the components of these huge cathedrals, as we said, which are Atlas and CMS today. Basically, you can never see these things anymore. They're all hidden behind things which are rather not so interesting to see, like shielding and cables, etc., as I told you. So if we go back to when we started to design these detectors, so this was like almost 40 years ago, to do research and development for about 20 years almost, the generic features which were required for these detectors were very, very, I would say, if you look at it today, it looks natural. If you go back 40 years, it looked almost impossible to build such detectors. And I will try and explain to you why, historically, and what has helped us with technology developments across time, over 40 years. We were fortunate that things have turned out in such a way that they actually work and beyond expectations. So the biggest unknown at the time was this problem with radiation. The detectors, I told you, I gave you examples during the first 2 lectures that basically nothing you buy in industry would survive in the Atlas and CMS caverns for more than a few months. Any laptop computer would just die very quickly. So this requires, of course, a huge amount of effort from within the collaboration, which we underestimated to a large extent, I would say, when we wrote up our proposals. To write that you will do all the work is very easy. Then you have to go and do the work, find the people to do the work. This is not that easy. And the radiation damage is all pervasive. It damages materials, even materials like Kapton, if it's not properly built, can be damaged beyond repair. So this is a very radiation-resistant material, but still it may not be enough in the regions of the detector where there is the most radiation. Electronics components are particularly sensitive to radiation damage. You may have heard about single event upsets, about damage to silicon, changing the purity of the silicon crystal, etc., through radiation. All these effects are very well understood today. They were not at all understood when we started on this. And so, for example, when we started to think about what to build for the LHC, some people said we will only be able to see muons. We just put a bunch of lead, of a very heavy material. We absorb everything except the muons and the neutrinos. But neutrinos we cannot measure, and then we measure the muons. If we had had such a detector, we would not have found the Higgs, almost certainly, because we would have no handle to measure the backgrounds. We would just see muons, but it would have taken at least many, many more years than it took us to find the Higgs boson. So we had to somehow be very optimistic and believe we could build calorimeters, which was felt to be maybe still possible. It was more a question of electronics. And we had to persuade ourselves that with a lot of research and development, we could also build tracking detectors which could survive the radiation. And in addition, this came from the US. It's not something which was thought of in the research and development for the For the LHC, this was the SSC, which was ongoing at the time until 1994. There was this parallel project in the US, which actually was born before the LHC was born, where a lot of effort was put by the US colleagues and Japanese colleagues in particular. And one of the experiments, in one of the experiments, there was someone who was very specialized in calculations of radiation using code developed for nuclear reactors. And this person found out that actually in the muon detectors outside, where there is, in principle, all the energy from the interaction is absorbed, there could still be a lot of radiation, basically from neutrons. And so you have to imagine that our detectors are sitting in a neutron gas all the time when the beams are turned on. These are very slow neutrons, and they can produce hits. They can produce signals in the detectors at such a rate that you can get background, which can even produce tracks because they can produce kaons, for example, charged kaons, which decay to charged pions. And then you see tracks and you think maybe I've seen a muon, but actually it's not a muon. So the whole experimental area is pervaded with this problem of radiation damage or radiation just present. The detectors should provide precise timing and be as fast as feasible. When I write new here, this was a new experimental challenge, right? We didn't have this challenge before at such a level. So 25 nanoseconds between bunch crossing was the smallest interval we had ever had. At Hera, the machine at Hera was not so far from that, at 100 nanoseconds, but with a much lower collision rate. So we had collisions for sure every 25 nanoseconds. You heard me, I told you that we have up to 60 today, 60 collisions every 25 nanoseconds in our detectors. So this was also new, and this means you need fast detectors, and you need, at least if you're not fast, to be very precise in your timing to be able to say, I saw a signal at this moment in time, right? Another challenge, of course, to try to measure as precisely as possible every single particle which is produced at the interaction point was to have excellent spatial granularity, again, beyond what had been achieved until then. The pixel detectors, which are in Atlas and CMS, it's the first time we had pixel detectors in Hadron Collider. And finally, we had to identify, and this is what happens always with higher and higher energy machines, the cross-section naturally falls with the energy in the center of mass. So the processes become more and more rare. And in real time, as I told you, we have to identify the events of interest. We have basically to throw away almost every event before we can even analyze them in our software, in our offline computing systems. So this is the challenge to our trigger and data acquisition system. The lepton identification, for example, leptons are rare, so they are a source of measurement because they can be measured precisely. We will discuss this a little bit today. I have limited time, so I'll go quickly through some of these things. They have to be found above a huge background from QCD, basically from hadronic jets, which can mimic leptons. And at the LHC, the ratio of leptons at a given transverse momentum of around 20 GeV or 40 GeV, typical for Z and W production, for example, is 10 to the -5, which is 100 times worse than it was at the tevatron. So saying that you could do this at the tevatron does not mean you can do it at the LHC. And the signal cross sections are as low as 10 to the -14 of the total cross section. So this is also, again, a new challenge. As I told you already a few times, the online rejection is required is about 10 to the 7, so that we can afford to send the data to our storage. And we have these huge data volumes to store to disk and tape. Despite the fact that people don't talk about it much, this is a challenge which is repeated every year at the LHC. We need more and more data storage. This is actually more of a problem than the CPU, the amount of computing time we need to produce all the simulated events to reconstruct our data, etc. The storage is really an issue, and we have to fight with our funding agencies to get the budgets to increase our storage capacity every year. Okay, so the detectors, therefore, must measure and identify according to certain specifications, and the Higgs boson was the most, I would say, benchmark process, the most rich benchmark process we had. We had, of course, supersymmetry searches, we had searches for exotic particles, standard model precision measurements, but the Higgs particle, with its abundance of production processes and decays, was sort of the measurement stick to compare Atlas CMS, to compare to Tevatron, to compare to SSC. You must understand in the history of the development of the LHC, the competition between Atlas and CMS. So colleagues here in India are all in CMS. In other countries, they're like Japan, they're all in Atlas. Other countries chose to go in all the experiments. There are even institutes in the world, very few, which are in all the experiments, which is amazing because it's a lot of resources you have to put into an experiment like this. If you want to make a contribution which is measurable, you can make very small contributions by parceling your activity everywhere. But if you want to be identified as a major contributor, you better pool your resources so that you do make major contributions. So institutes, depending on their culture and history, had varying strategies. So the Higgs boson, through its various decays, puts challenges on basically all of the aspects of the measurements in the experiment. And a final requirement, which is not so unimportant, is the detectors must please. I was asked a question yesterday, why does CMS have all silicon and why does Atlas have a gas detector? There is no answer which is scientific 100% to this question. It's a sociological, cultural question of what people have as experience when they come into the collaboration and say, I want to participate, I want to build something. They have some past, of course, some past history, some experience, some ideas, etc. So the technology choices which were made were sometimes difficult. They led to heart-wrenching decisions for the collaborations. And sometimes they were easy because there was a sort of focus immediately on one way of doing things. It doesn't mean it's unique. And actually, this is the richness of Atlas and CMS together, that together they confirm each other or not. We found some supposedly interesting possible new physics signals. It almost never happened in both Atlas and CMS at the same time. Happened once at 750 GeV, some gamma fluctuation, and then it died immediately when we had more data. And it still gave rise to 400 theoretical papers in a few months, of course. So this is the fact that theory is not reviewed as much as experimental papers. So the funding agencies also must find it pleasing. So a funding agency, unfortunately, finds it pleasing only if you don't spend too much money. So originally, you may find this amazing. The Director General of CERN said Atlas and CMS will cost 475, notice the 1% precision, million Swiss francs each. So first, they should cost the same is impossible. If you think the probability that Atlas and CMS had the same cost, it's 0. They have different costs, but no one knows really how much was the real cost. We know approximately the real cost. And this is because if you think of how to compute the cost of something built in India, plus Russia, plus America, plus France, and all this, with different ways of counting money. So some countries like the US, they count the salary of every single person who works on anything in the experiment. In Europe, we don't count the salaries of the people who are paid by the government in the budget. It's they're paid anyway to work, so you don't count that in the budget. In the US, you do. So you have to somehow mix all this in a proper way, which is the magic of the financial managers of the experiments. And of course, they work for the experiments, so they try to make the costs appear to be as small as possible. But the reality, who knows, So I don't know really what the cost was, but it was certainly more than this 475, at least twice more from the numbers I know. And finally, and this is important to you, especially for your future, the young physicists who will provide the main thrust to the scientific output of the collaborations. So in Atlas and CMS, we have typically 1,000 PhD students, right, who are doing their work at a given moment in time. 1,000 PhD students is such a huge thing. And they produce a lot of scientific output. And how does one recognize individual contributions? This is, of course, an ongoing problem, which is very difficult to solve, and there's a lot of effort put in all the collaborations to answer these questions. So if you're interested in reading something about, Govinda mentioned it, with Paris Ficas from CMS, we wrote an article some years ago, just presenting what Atlas and CMS were before data taking, where a lot of this is discussed. So here is a little bit of a cartoon of what happens inside our detectors. If we want to detect an electron, what we want to do is we want to see a track in the tracking detector. Sometimes this track is perturbed because it crosses material inside the detector, especially with electrons. But then the electron has an electromagnetic interaction, so it interacts quickly, and it produces a small, let's say, amount of energy, a small in space amount of energy. It releases all its energy in the electromagnetic calorimeter, essentially, and only a little bit in the hadronic calorimeter behind. That's why they're called electromagnetic and hadronic calorimeters. Behind all that, you have these muon chambers with some sort of magnetic field, and you measure the momentum of the muons in addition to measuring it with the tracks of the muons. So I go a bit quicker now. A photon is like an electron, except there's no track. In general, of course, with the amount of material I showed you yesterday, we have in the Atlas and CMS trackers, in some regions, more than half of the photons convert into an electron-positron pair, and they behave like this with two tracks in front of the electromagnetic calorimeter. Then you have the bulk of the particles are charged pions, they're kaons, charged kaons, protons, whatever, and they give a track in the unit detector. And if they're energetic enough, they give a big shower also in the calorimeters, but both hadronic and electromagnetic. And this shower in space is much bigger than the shower from the electromagnetic particles. We have the neutral kaons, the neutrons. These are the particles which actually limit the precision with which we measure jets, for example, or charged hadrons if we look at an individual charged hadron, because we don't have a measurement of their momentum. We just have the energy in the calorimeter, which is less precisely measured. And finally, we have the muons. And the neutrinos, which I put there just as an additional particle, which is, as you know, as we discussed, is measured through, in the transverse plane, at least through the absence of balance of transverse momentum in the event. Okay, so if you look at the cross sections, to give you a number, sort of number of the selection power which was required for the Higgs discovery, it's about 10 to 14 to 10 to the 15 rejection in order to get from the total cross-section to the Higgs cross-section. You see the Higgs cross-section here. At the time, we had various Higgs masses because we didn't know. So 100 GeV, it's here as a function of the machine energy. So Fermilab, LHC, SSC are shown by the vertical arrows there. The LHC was 20 TeV in design. And of course, it's never going to be 20 TeV. It's at 13.6, so it's slightly below, and it started even lower, right? At 7 TeV, even below 10 TeV. And the Higgs at 500 GeV has, of course, an even smaller cross-section, irrelevant today. And then you have all the background processes, which are shown here, and in particular, the jet cross-section, which is many, many orders of magnitude above the Higgs cross-section. So LHC, we talk a lot about Higgs factories today for the future. actually the world, the particle physics community has tried to sell machines to be built to the funding agencies for more than 30 years, calling them Higgs factories each time. So it's easy to call a machine a factory. It can produce many events, for example, but you can only see a small fraction. This is typical of a hadron collider. In a hadron collider, we produce, for a Higgs mass of 130 GeV, 0.04 events per second, so 100,000 events in 1 year. But the fraction of Higgs events we found with 100,000 events produced was very, very small, because the branching ratios are small and we have efficiency limitations. We don't trigger on every single event, etc. So the factory is a bit of a subjective word. And actually, for the future, to say that we have Higgs factories, they are not Higgs factories if I compare to the LHC in terms of producing Higgs boson. They can be Higgs factories for specific channels, for di-Higgs production, for things which will not be measured very well at the LHC. But as I told you yesterday, the gap between what the LHC will have done by the time it reaches in 20 years or so, the end of its program, and what can an E plus E minus machine bring as additional information on the Higgs boson, this gap has become very small and becomes smaller and smaller with time. I don't know, many of you are not necessarily from a high energy physics background, I believe. So there's a lot of things we take for granted when we talk. So Emil, for example, is very clear on this in his lectures. I think also as an experimentalist, we have to be very clear to students that when we talk about particle reconstruction identification, we often make shortcuts because we're used to it. For example, we think relativistic, and we only talk about relativistic particles. A typical example is that at collider energies, muons, we call them stable particles. We really, in our code, they're called stable particles, but they're not. They decay to electrons, right? But they never decay while they cross the detectors. I showed you a picture yesterday. You can have many, many interactions which proceed through the detector over 25 nanoseconds, 50 nanoseconds, etc. The light speed is not enough to take us through the detector, even for a fully relativistic particle, because the detector is huge. But a muon has no time to decay, even though the detector is huge. So some particles are considered as long-lived. So Emil showed you an example, sketch, for a B hadron, because it has, like the tau lepton, lifetime which is long enough that one can see its vertex far enough away from the primary interaction vertex that one can identify this with some efficiency. It requires excellent accuracy, and that's why you asked me a question, someone yesterday, that's why we have pixels very close to the beam, so that we can have very performant identification of long-lived particles. And all the other particles in all this wonderful standard model zoo can only be seen through their stable decay products. Okay, so what do we really see in the detectors? What we see is basically what comes out of strong interactions. We are colliding protons, so we have QCD, which drives everything, which is very painful to compute for theorists. So I told you yesterday, they like to compute supersymmetry. They like to compute Higgs because this Higgs has spin 0. It makes things easier to calculate, et cetera, et cetera. But QCD is very difficult, especially at the orders which we have achieved today. We require n-cube-LO accuracy, which means order alpha S cube for the production of Drellian processes, which are measured very precisely at the LHC, production of Z's and W's. And this is a huge computing effort and also brain effort by theorists to produce calculations which meet our requirements and which are accurate enough, even though they will always be less accurate than the measurements we do with the leptons from Z's, for example. So the particles we see are essentially the hadrons coming out of quarks and gluons, which do not go far. This confinement you heard about. And the hadronic jets contain basically mostly charged pions, but also all these other particles. Then we have soft processes, which materialize as a uniform soup of charged and neutral pions, kaons, etc. The soft processes are the ones which produce all the extra interactions and which just are basically noise in our detectors. Now, coming a little bit to the environment, we have to understand the machine a bit. So if you look at the environment of the LHC, and we discuss luminosity, luminosity is basically the intensity of the beam, right? And if the beam have zero crossing angle, then one can write down the luminosity in a simple formula, let's say for designing an experiment, where you need to know the distance between bunch crossing, delta T, 25 nanosecond, the number of protons you have in each bunch, about 10 to the 11, the energy of the beam, and a function which is called the beta function at the interaction point, which gives you the size transverse to the beam direction of the beam. So the smaller the size of the beam, the more intense the interactions will be. So the luminosity is inversely proportional to beta, which has gone down by now even to 0.3 meters, the highest luminosity of the LHC. So there are quadruples in front of Atlas and CMS, which basically provide this function of minimizing the size of the beams in the transverse plane. And there's also a parameter called the emittance, which is basically characterizing the growth of the beams as they circulate across the tunnel. They don't stay of the same size eternally. So the emittance has to be very small, such that the beams can have a long lifetime, and we can keep the beam in the machine for as long as possible. So now, if you take the luminosity, which is given to you by the machine, you can compute the average number of particles, which is produced per bunch crossing. And this is a simple formula too. You need to know an inelastic cross-section, so the probability that the two protons break up and produce for you a hard interaction, let's say a soft interaction, but an inelastic interaction. And then you have to multiply by the bunch spacing and divide by the emittance of the bunch. So at the LHC, we get something like 23 at 10 to the 34 inelastic interactions per bunch crossing. And we have gone way above, as you know, to 10 to the 34, so close to 50 or 60. So this is a huge change compared to previous machines. And this was something on which we had to have nightmares all the years of R&D about how we were going to deal with this. At LEP, of course, the times were very, very much longer, and the average number of interactions was very small. So basically, there was no trigger problem, no problem of pileup, nothing. Where we discovered W and Z, this was also a very small problem. HERA was as close as you could get to the 25 nanoseconds before the LHC started, but had almost a very small number of interactions per bunch crossing, and Tevatron went up to about 2 or 3 interactions per bunch crossing at the highest luminosities, but had 400 nanoseconds between bunches. So a big step in the future forward into the unknown. So from the average number of interactions, this is the experimental environment, and the physics machine performance determine this. You can determine how many charged particles you expect in your detectors. You can determine the energy you expect to be deposited in your calorimeters. And we needed to know all this to do the research and development to build the correct detectors. And you can even compute the radiation doses in terms of ionizing radiation and also of neutrons, as I told you. And then you can study pileup meaning extra events which cause noise in your detector. The pileup can happen in time and it can happen in space. And you saw examples. I showed you real events reconstructed with a Z to E plus E minus. I showed you an example in Atlas with an extra 15 other interactions reconstructed at the same time, where you see the particles emerging from each of the interactions and you see the 2 leptons from the Z decay. So detectors are able to do this. But of course, in those days, we weren't sure we would be able to achieve what we have done. The interaction point being represented here if you look at the types of interactions you can have elastic interactions, which won't discuss today, which are studied in some of the very forward detectors of the experiments or specific experiments. The inelastic interactions give you particles which emerge from the beam pipe, and based on that, you can trigger on these interactions in a very simple way, and you can then try to measure the properties of these events and also predict what you will see. So the inelastic cross-section at the LHC, this was done before we had data. By now we have data with very precise measurements of the total cross-section, in particular from Totem, which is a sister experiment with CMS. And we have similar measurements from Atlas. And we know things about the total cross-section and some specific aspects of its behavior, which we didn't know, of course, at the time of the R&D for the LHC. When we talk about, I don't know how many of you are familiar with the concept. So how many of you are familiar with the concepts of rapidity, pseudo-rapidity? Can you tell me? Okay, about half, yeah, good. So it's probably not useless that I say a few words, spend 1 minute on this. And it's also a very important aspect of development of calorimeters, for example, or even of silicon detectors, etc. That if you look at the features of the physics of the soft interactions which define the rates you will see in your tracking detectors or in your calorimeter, basically the average number of particles per unit pseudo-rapidity, which is basically the pseudo-rapidity is represented here. You see on this axis, minus log tangent theta over 2, where theta is the angle between the particle and the beamline. So you can relate pseudo-rapidity and angle, very large pseudo-rapidity, very small angle, right? So at 14 TeV, say, which is almost exactly the energy we have now, you have a constant rate of particles per unit pseudo-rapidity up to very, very high rapidities beyond what we can measure, right? The detectors measure up to here. And that was determined by simulation. We needed to measure up to here to be able to capture most of the transverse energy in the event. And then everything beyond, we don't measure. And this feature is very important because it tells you that the physics is very important. It's not a general feature, but for the design of the detectors is about constant versus eta at fixed PT. So this is very important because, for example, it tells you that if you build a calorimeter cell with all the same size, if you want to build a detector, you don't want to build every single component with a different size, so it costs way too much. So if you build it with the same size in a cylindrical geometry here, then you will get the same rate of particles across each cell. And that's, of course, a very nice feature to have. So in Atlas and CMS, we had all this work done to try and understand what we would need to do in terms of the rapidity coverage of the detectors. So here you see, for example, the charged particle multiplicity, how many particles we produce from inelastic interactions at 14 TeV. So around 8 per unit rapidity. And here is shown the average PT for an average PT with an average PT of about 500 MeV. Then you see that Atlas and CMS cover this region here. And what is outside, we basically don't see. And these are pictures of what the models were predicting at the time, giving very large differences sometimes between what they predicted and what we eventually saw. But they were not so far off. So what do we expect then in terms of what the detector will have to suffer in terms of radiation and in terms of load of signals it has to deal with? What we expect is that about, as I just showed you, 8 particles, charged particles per unit rapidity. We expect these to be charged pions mostly with an average PT of about 0.6 GeV. And in terms of neutrals, we expect a similar number because we have charged pions and neutral pions, but the neutral pions decay to 2 photons. And those come from pi0 decay, the photons, and the PT therefore is about half, about 0.3 GeV. And if we take a detector coverage for the tracking part of the detector, which was smaller than 5 units, which is about 2.5 units in Atlas and CMS today, which will go up to 4 units in the upgraded detectors in a few years, this goes down already to 6 degrees from the beamline. So it's not so easy to build such a tracking detector. And the calorimeters go down to 1 degree from the beamline. So this means that the very forward part of our calorimeter in Atlas, it's close to the interaction point. It's about a centimeter. It's very close, centimeter from the beam pipe. We are measuring calorimetry with huge amounts of energy going into it. So most of the energy is not seen. About 300,000 GeV of the energy goes down the beam pipe. We have about 900 charge tracks every 25 nanoseconds through the inner tracking. We have about 1,400 GeV transverse energy, which corresponds to about 3,000 particles in the calorimeters every 25 nanoseconds. So these are the basic numbers which define the specifications for the detectors to be able to cope with the loads they would see from signals which are not interesting, such that they operate stably. This is just a question of survival, right? Survival and having a performance which is not affected by this load. Two aspects, right? Surviving and the performance being unaffected by the load, which is essentially noise. So if you look at this example of a CMS event with high pileup with all these tracks, so it's basically black, right? You don't see anything. It's unfair to show it like that. What you should show is a small slice. I have seen a vertex here, for example. So I look in the transverse plane to the beam now, and I look at what this event per superposition of events looks like. It's still much more complex than an LEP event. So E plus E minus physics is, that's no doubt, cleaner than Hadron Collider physics. But also today, we know there's no doubt that despite this, Hadron Collider physics provides measurements which are competitive or better than E plus E minus. We see this, for example, with the W mass measurement. It's not LEP which dominates the W mass measurement average today by far, even though we have some problems with Hadron Collider measurements, W mass, that's another topic. So radiation resistance of detectors, this was for 20 years for many of us, for me in particular with a gaseous detector, as I told you yesterday, an aspect of detector R&D, which we didn't know almost anything about. And in particular, we used military applications for electronics chips in the beginning, because this is the place where there was knowledge about this. And also we used computer code, which was developed for nuclear reactors. For example, in places like France, the US, etc., we had very sophisticated codes to predict the amount of neutrons present from interactions and their transport, especially through matter. This was the most difficult aspect. The ionizing radiation doses and the slow neutron fluences in Atlas and CMS are almost entirely due to the beam-beam interactions and can therefore be predicted. This is a very important point because it was not the case in recent and ongoing machines at the time, like Tevatron. The radiation dose at the LHC is so huge that basically, if you have only 10 to the minus 7 of the protons in the beams in the vacuum of the beam pipe of the LHC, which escape, then the magnets, the superconducting magnets, would quench immediately, and you would lose everything, and the machine would have to restart, or you might even break something. And it actually happened, right, for a different reason. But so the machine was designed such that this would not happen. And it worked, actually. This works. We can predict the radiation. We have shown that what we predict matches what we see. This was absolutely not the case before. Before, in Tevatron, it was sort of random occurrences which would cause like the beams being lost one day, and this caused radiation. And this is basically how you could calculate the radiation which was present in the environment. So it was not a predictable thing. And we used this nuclear application. So here is an example from many years ago of the neutron fluences expected in Atlas. So there's some units used here per square centimeter per year, typically, to give you an idea. 1 MeV neutron equivalent. This is because one has to also look at this for doses from other radiation, ionizing radiation, and transform it for silicon detector survival into a unique number. And this is the color code, tells you the rates. And when you reach rates, so let's say laptops and commercial stuff, they start to die around here. So anything above the green color will die in less than 1 year at the LHC. In terms of damage, I hope you're not too bored by me talking about radiation damage. It was a topic which is now basically not so much existing except for future detectors at the LHC. For the existing ones, they seem to have, they have survived, they have kept their operational properties. So they were designed with safety factors. And this is fortunate because they have already taken on more load than they were designed for initially. So the damage can be caused by ionizing radiation. This is caused by energy deposited by particles in detector material. A typical number is 2 MeV per gram per square centimeter for a minimum ionizing particle. So this is, there was a question to Maxime about how much energy do particles lose. It's a very small amount of their energy if they have GV energies, but it's sufficient to do damage if you have many, many of them. They're also caused by photons, created electromagnetic showers, and it's proportional, the damage is proportional to the deposited energy or dose measured in gray. The gray is 100 rads. So basically, the numbers we had to face, there was one ballpark number, 2 million gray, divided by the transverse distance to the beam squared, because the radiation is hardest, is most abundant near the beams per year. And that was our target. The damage can also be caused by neutrons. The neutrons are created in hadronic showers in the calorimeters, and even more so in the forward shielding of the detectors and in the beam collimators themselves, where most of the energy is dumped. This is where you get a creation of a huge amount of neutrons. Only? Wow. Yeah, so I won't go very far in this lecture, but it's okay. The expected neutron fluence is about 3×10⁻³ per square centimeter per year in the innermost part of the detectors. Okay. I'm going to finish this part gracefully. I'm not going to start galloping like a horse. The lecture, I will put the lecture on the website. You will see the rest of it afterwards. So neutrons are particularly dangerous. You can take somebody. It still won't be. I'm sorry, I was just slow in this, but I wanted to be very clear. The neutrons, they wreak havoc, they destroy semiconductors independently of the deposited energy because they modify directly the crystalline structure. So this is why the need for radiation hard electronics with military applications was what was required most in the early days. And on the other hand, most organic materials survive easily, reasonably easily up to the required doses. So the material validation and quality control during production are needed at the same level as for spatial applications, because there's no way we can go and repair anything if something goes wrong with this. I'll give you one example in Atlas, which was sort of sobering for us. When we started construction in about 96, 97, 98, there was sort of suddenly a phase transition in the collaboration. People stopped doing R&D a little bit and started to think we have to build. So let's stop and let's start to build. And some people did it faster than others. It's always very difficult for physicist type brains and engineers to go into production, because you always think you can do better, more work, improve. And it's a phase transition, really. So phase transition happened, and the hadronic end cap calorimeters went into production first. And they produced 8 modules in 1 year, which they brought to the test beam at CERN. And all of us, me in particular, we were jealous. You know, these guys have already produced things for the experiment. We have nothing, and we won't have still for some years. And then they tested these modules in beam. And intense beams, and they found suddenly that they were short, the high voltage was dying. They were getting shorts in the high voltage. And this was unforeseen. And so they had to backpedal. They had to take them back to Max Planck Institute in Germany, in München, and they took the modules back. They took them apart, and they finally identified the reason for this. And the reason for this is, of course, very hard to sort of prevent it to happen in a hugely complex experiment. The reason it was a kapton, which kapton is an insulating material, very good properties. A kapton, which was used in the production of the boards to deliver the high voltage, which was produced in Russia by people who were helping to build this calorimeter, by a supplier who changed the kapton without telling people the type of kapton. They changed from one kapton, which had been tested to be okay for high voltage, to another one, which was not okay. And suddenly you break everything with such a small event, right? So this gives you an example of what quality control means. We wrote, I told you the first day, we wrote a lot about quality control without understanding at all what it meant in terms of the amount of manpower and work we would have to put into it. And then we had to do it, and we had to find people, we had to find software, databases, all sorts of stuff so that we could track things and be able to understand what was going on with the construction. I think I will probably have to stop in the middle of something because, yeah, maybe I finish with, I showed you yesterday an example of a J psi K short decay, so something which is useful to measure the beta angle, right? The J psi K short. Here I show you another type of event. So this is a Higgs to gamma gamma, where one of the photons, I told you it happens very often in Atlas CMS that unfortunately the photons convert before they reach the calorimetry. If they don't convert, you see something very beautiful. And it's even more beautiful in CMS because CMS has a crystal calorimeter which has very high resolution. So you measure with the capacity, intrinsic capacity of your calorimeter, basically. But when the photon converts, it becomes ugly. This shower looks like it has two peaks, and it actually does because the photon converts here, and you see two tracks in the TRT detector. So this detector I worked on for so long, and these two tracks produce an electromagnetic shower, which has actually two components in it, the two electrons. And okay, this is where I stop with these lectures. Maybe I say a few last words. I hope they gave you a glimpse of what we went through to build Atlas and CMS. I hope that you got a feeling also how exciting it is to develop a detector for a new experiment, a new physics go. It's an intrinsic part of being an experimentalist to do this. So I'm very glad that these lectures have many people. And I just couldn't go through, you know, how exciting it is to do the operation itself. I gave you a few examples, but the operation is very exciting to spend hours in shift and seeing the data going through the detector. And finally, the physics. This is not the main topic of the school, of course, the physics, extracting Higgs physics. All the measurements we did at the LHC was a huge reward. And the discovery of something, as I told you in the first lecture, is nature decides. And we are lucky those who actually are there when it happens. Thank you very much.
Thank you, Daniel. Okay, so my personal view is that there is many things written in the textbook you people read, but I was expecting, and you really deliver that in the experiment. What are the nitty-gritty integrity which is not given in the textbook, but as an experimentalist you need to know that, and that's the glimpse you have given here. And I hope people will now understand that really what is the experiment. This is not just a simple textbook what we read. This is a much beyond that. Yeah. Okay. Then any question to Daniel?
Very good presentation, Daniel.
I'm sorry.
Yeah.
Okay, so my question is that you mentioned several times that the detectors work for a longer period than expected. So my curiosity is that was it our aging studies that were the problem in the expectation of the lifetime, or there was some other effect due to which a detector managed to survive for this long?
Yeah, it's a good question. So I'll be honest with you. I could say that, of course, we had safety factors built in, which we did. We did have safety factors built in, especially for the electronics. So we first took a safety factor about a factor of 2 on the physics, because the physics of these soft interactions we didn't know. So when we say the detector was designed for 100 inverse femtobars, which we already have, it was actually 200, which was put into the simulation. That's one safety factor. Then another safety factor, I'm talking about Atlas, but I'm pretty sure CMS had similar. Then for the electronics, we added a safety factor of factor 5, because basically it was rather new things to understand how electronics, microelectronics chips worked under radiation. So there's like factors of 10 or 20 on the electronics. Then I think a further answer to your question is that we knew that most of the detectors would die gracefully. So that, for example, a silicon detector, what will happen with radiation? Its leakage current goes up. And for this, you have a power supply, which you've designed to be able to let it go up and still provide the power such that it will work. But then you have intrinsic things which happen with the behavior of the silicon, and you lose efficiency to collect the electron pairs. And this efficiency loss will result in an efficiency loss in reconstructing tracks. But this is something very graceful, very soft, because you have many hits per track. So you lose one layer, it doesn't matter that much. When we were designing the detectors, we had to be very careful, because then someone would tell us, but it will cost less, so just remove a layer. And then we had to show, if you remove a layer, then in this case, this will cause a big effect. So it's sort of a schizophrenic behavior. But basically, it's these safety factors, plus the fact that I think the physics actually was exactly more or less as we had predicted. So this factor 2 in the physics we didn't need, for example. I hope I answered you.
Thank you, Professor, for your nice presentation. How the building up of detector free from pile-up is possible, since the another particle is in queue before the detector displays the previous particle. What are the attributes that have the high influence of the pile-up effect?
That have what?
Pile-up effect.
Yeah.
How that pile-up effect? Pile-up effect. You discussed here about the pile-up effect. And another, my curiosity is just, you keep different interesting pictures just before delivery, before starting your lecture. Is there any scientific correlations with the work, or something else?
Background, someone girl sitting.
That's my daughter. That's my daughter. My daughter in Vietnam, in Halong Bay. So your question is about pileup, but I'm not sure what you want me to tell you about pileup. I think pileup is something which is part of our lives at the LHC, but which we slowly forget about, except if we work on it specifically in the performance groups or in the future detector building, because at HLLHC in a few years, it's still a bit far away, right? But still 5 or 6 years from now, we'll have new tracking detectors in Atlas and CMS. Even CMS is replacing end-cap calorimeters, a huge work, right? And their pileup is still a huge concern, because now we go to 200 events of pileup, not 50, 200 or more. And it's being treated, if you want, as a stochastic noise, a little bit problem, because we know now the physics of pileup, so we're sure about the physics. And what we have to deal with is basically the noise it produces, which distorts the response of the detector. So pile-up is part of our lives, but if you work on physics as a PhD student, you will tend to forget about it. If you work on performance, like how well I can reconstruct a jet or an electron, which is sensitive to pile-up, then you will have to deal with it because you will perhaps want to improve the performance. But by now we have 10 years of work already put into improving the performance. We use machine learning to help with pile-up, with physics. Machine learning, you will have lectures by David on this, is the enemy of physics. If you are interested in machine learning more than physics, you should go to IT and not to physics. Machine learning is just a tool, right? And it's just a tool, and it's not more than that. And beware, if you use machine learning, which we do heavily by now, because it does improve things, of course, there's no doubt. But you have to do much more validation work to use it, to prove that it doesn't distort your physics result or produce false positives or whatever signals, you know. You have to do much more work than if you use simpler things. So we start to use it now in the reconstruction of the detectors or the identification of particles, but it's not mature yet. For it to work with pile-up, it requires a lot of work.
Thanks, Daniel. My responsibility on the rear of the institute. Our art collection. This is our tradition. This usually we
I've never seen this before. No, I saw it yesterday. Thank you very much. Thank you. Thank you so much.
And also the side, that is a small art collection to you. This is our local tribal printed it.
Thank you. Thank you. Very beautiful.
Thank you.
Thank you, Govinda, and thank you all for the hospitality of TIFR, of India, which is a wonderful country. And thank you very much again.
I will see you again some other meeting.
Well, this afternoon, right?
Yeah.
This afternoon, really.